All right, in this example, we will find the equivalent impedance of this particular example circuit. In this circuit, we have two resistors, a 1 ohm resistor, a 3 ohm resistor, an inductor that's 3 Henry, and a capacitor that's 1/3 of a farad. And this is AC steady state. Since we're trying to find impedance, the frequency of the oscillation is given as 1 radians per second. So we have AC signal oscillating at 1 radians per second. That's the omega that we're given, and we're asked what's the equivalent impedance. Okay, so to get started, in order to find the equivalent impedance, first we need to uh, write down the equivalent impedance of each of these components that we have here. Now the resistors, the equivalent impedance of those resistors are the resistances themselves. So 1 ohm, that's the equivalent impedance of that. 3 ohm is the equivalent impedance of that resistance right there. Now for the capacitor and the inductor, we'll find the equivalent impedances by using these formulas. The impedance of a capacitor is given as 1 over j omega c. Since 1 over j is the same as minus j, we can rewrite this as minus j over omega c. Now omega is given as 1 radians and c is given as 1/3. So plugging those values in here, we get the following minus j3 ohms as the impedance of the capacitor. Moving on to the impedance of the inductor right here, inductor impedance is given as j omega L. Omega is 1 and the L inductance value is 3 Henry, so we end up with 3 ohm, j3 ohm impedance right here. So what we end up with is, instead of Henry and farad values, let's just denote them as impedances. So we'll end up with uh, the following. So we end up with this particular circuit that we just calculated on. So we just calculated all of these impedances right here, and we're going to replace them here. Now, as I take a look at this, I see two things. First, I see that this 3 ohm resistor and this J3 ohm impedance, so 3 ohm impedance and J3 ohm impedance are in series. So I can combine them with the knowledge that series impedances add together to form a total impedance. So that becomes 3 plus j3 ohm from 3 plus j3 ohm from these. Now, I notice that this two impedances are actually in parallel with each other. So the reciprocal of these, so the equivalent 1 over the equivalent of these two is equal to 1 over this plus 1 over that. Another way of saying that is the equivalent impedance here between these two parallel. So the parallel impedance here is this impedance times that impedance divided by the sum of these two impedances. Okay, so that's what we have. Now let's simplify this. So I see j3 minus j3, which leads me to simply 3 in the denominator. Next thing I see is that the 3 and 3 here can cancel on the numerator and denominator, so I'm left with simply 3 plus j3 times minus j. Uh, let's distribute minus j throughout. So what I get is minus 3j's by multiplying against 3 and minus j. j3 times minus j, which gives me this right here, and that brings us to minus 3j plus minus j squared over 3 times 3. J is a imaginary number, and j squared is actually minus 1. So minus j whole square is equal to 1. So I end up with 3 minus 3j as the parallel impedance right here. Now, if I observe carefully, this new parallel impedance that we just calculated for these two units is in series with this 1 ohm impedance when we look at it from this terminal. So from this terminal, we see a 1 ohm, and then we see this parallel network. And this parallel network is in series with this 1 ohm. So our equivalent impedance is 1 plus this parallel network we just calculated, which is 1 plus 3 minus 3j. So that gives us 4 minus 3j ohms. Now that's the equivalent impedance seen from the terminals. Now if we wanted to write this in polar coordinates, so these are Cartesian coordinates, and if we wanted to write the polar coordinates, we can convert them by taking 4 square plus minus 3 whole square, take the square root of that. That gives you the polar magnitude right here. And the angle is arctangent of -3/4. And if we do this using our calculator or MATLAB or your favorite tool, you'll end up with the equivalent impedance in polar form as 5 with an angle of -36.86 degrees ohm. Okay, so that is the equivalent impedance seen from the terminal for this particular circuit.